In this video, we're going to discuss the atomic radius and look at its trend throughout the periodic table. Now, thanks to the Bohr model, we largely view atoms as circular, spherical. So the atomic radius is really looking at the size of the atom, right? So each atom is going to vary in its different sizes, and the atomic radius is a way that we quantify that difference between the size of different atoms. So here I have two examples. I have two atoms here. The one on the left, the purple sphere on the left, is lithium, and the blue sphere on the right is fluorine. And what you'll notice is that lithium is significantly bigger. It's a significantly bigger atom than fluorine, right? So lithium has an atomic radius of about 152 picometers, and fluorine has an atomic radius of about 64 picometers. Why is that, right? So again, I picked these two since they're both on the same row of the periodic table, and their valence electrons will be in the same principal quantum shell, right? So let's take lithium for example, right? If we're to draw like a Bohr type diagram for lithium, we would have its 2s orbital on the outside, and it would have that one electron in the 2s orbital, right? So this would be our 2s orbital for lithium, right? Now, again, noting the difference in the number of protons here. Again, lithium will have 3 protons and fluorine will have 9 protons. And that difference in the amount of positive charge in the nucleus is going to come into play here again to describe the size of each atom, right? So I'm going to try to kind of draw this to scale, right? So this is the 2s orbital for lithium. Because of the significantly higher number of protons in fluorine, there's going to be a greater Coulombic attraction between that nucleus and the electrons, and that's going to draw the electrons a lot closer to the nucleus. So let's put the 2s orbital for fluorine, let's put it here, right? And we know that fluorine would also have a 2p orbital as well, right? And let's pop some electrons in there. We got 2 in the 2s, and we got the 5 that are in the 2p, right? So because fluorine has more protons, it's going to have a greater attraction to those electrons, and so they're going to be a lot closer to the nuclei, thus creating a smaller atom, right? So when we're talking about the size of the atom, we're not just talking about the nucleus, we're talking about the space that the electrons take up as well. And if there are more protons in an atom, then it's going to have a much smaller total atomic size because it's going to contract those orbitals or I would say, just bring the electrons closer, right? In contrast to an atom with less protons. So there will be a significant size difference here between lithium and fluorine because of that contraction of the electrons closer and closer to the nuclei. So let's look at the overall trend, right? So going across the periodic table, going from right to left, the atomic radius increases, and then going down a column, the atomic radius increases as well. So this is like the opposite trend of the electron affinity and the ionization energy. The further you go to the left on the periodic table, you get larger and larger atoms, right? So this going from right to left is explained by the same mechanism that we just explained, this difference between fluorine and lithium. As you go to the left on the periodic table, you start to get less protons in the nucleus, so those electrons are going to spread out further since there's less positive charge to attract them. And then going down the periodic table, you get larger atomic radius as well. You get larger atoms because the electrons are being added to higher and higher principal quantum levels further away from the nucleus, right? So, for example, comparing the 1s electron in hydrogen to the 4s that would be in potassium, right? Potassium is going to be a significantly larger atom because it has more electrons that are populating larger and larger principal quantum shells, larger orbitals. So it's going to have a much larger size. So that explains both of the trends of atomic radius for atoms using the periodic table.